The interceptor got it. Okay.
So just to get a show of hands, who here plays chess or used to play chess? Oh, okay, this is gonna be fun. Great. So today I'll be talking about writing systems that apply to chess and other games as well. So here's how the outline talk is going to go. We first introduce chess for whoever here that has not played the game before, and then we want a motivation for why we want a rating. Then we'll talk about a predecessor of the yellow rating system, which is the Harkness rating system. We'll show how the calculation is done, and how some problems might want to push you to go for a different rating system. And then we'll give a derivation of the ELO rating system, which is an amendment proposed by ELO to the Harkness rating system, which about how the calculations are done, and which involves the logistic curve. And we'll show how to derive this curve, how it naturally follows from the win-loss ratio in a sense. And then we'll talk about some other methods of ratings, other methods of assigning a numerical value to someone's playing strength. Now that modern day engines that are capable of playing almost perfect games are available. And we'll talk about some of the problems with comparative ratings against other players, namely inflation, and a computer assisted rating such as average centigram loss. So here's how chess works. It's a two-person game. It's a deterministic game. There's no roll of the dice or flip a coin. It's a zero-sum game. You cannot have both players winning. Either one of them wins and the other loses, or this game is also a draw. And when you play a tournament, you are assigned a score to every game you play. If you win, you are usually assigned a score of 1. If you lose, you're assigned 0. If you end up drawing this game, it counts as half win and half a loss. And just for simplification purposes, let's not consider that situation for now. Let's just pretend that all chess games must end in either a win or a loss. And the question is there a reasonable way to assign a single number that captures how skilled a certain player is? This number would be the basis of the rating system. First, the Harkness rating, which is a really old system that was adopted by the USDS, the United States Chess Federation, that is between 1950 and 1960, before it was finally taken over by ELO's new rating system. And this rating is calculated after each tournament you participate. And this rating only takes account into 2 factors, namely when you play in a tournament, you might say you play against 5 different opponents. This rating takes into account the average rating of the opponents, which we denote by R sub A, and your average personal score against these opponents, which we denote as S sub A. Notice that S sub A being an average of scores between 0 and 1. Between 0 and 1. And here is how the rating is calculated. We take the initial, we do not consider even the initial rating of the player. Instead, we just take the average rating determined, which will be the basis for your new rating post-tournament. And we add this term 1000 times S sub A minus 0.5. And you can think of this term S sub A minus 0.5 as being, on average, how well did you outperform your competition? And if this value is positive, then your rating would be higher than the average rating of the competition. But if you manage to, say, on average, lose more games than win, then your new rating will be lower than the rating average of your competition. Seems pretty reasonable for now, right? Well, actually, there are a couple of problems to the system. Here's the formula again. First, it's quite volatile. This entire rating depends not on your cumulative history as a chess player, but it just depends on the result of a single tournament. So if you significantly overperform or significantly underperform, you're going to be stuck with this rating that is not truly representative of your strength as a chess player. There's another problem, which is that it's recalculated after every tournament, where ideally you might want to have your rating updated after every single game. There's another problem that is arguably a bit more concerning. There are these super counterintuitive outcomes outcomes where you could say lose every game in the tournament and gain rating points compared to your previous rating, which on common sense level should not be possible. And here's how it could happen. Imagine that you had a really high initial rating previous to the tournament. And then you come into this tournament and all of the opponents are much, much lower rated than you are. So if you take this formula and imagine you won every game, S sub A would just be 1. And the maximum rating you could possibly get, even if you win every single game, is the average rating of your competition plus 500. So if the average rating of your competition is 500 points more below your current rating, you're going to lose rating after winning every game. And conversely, the opposite could happen too. You could start with a really low initial rating, but you attend this tournament that's way beyond your level, lose every game, and gain rating points. That should not be possible. So in the 1960s, the USCF asked this yellow person to come up with a new rating system. Interestingly enough, in addition to a chess player, our Pablo is also a physics professor. And the objective is to estimate the current playing strength of the player based on very few important factors, which include outcomes of games you've played and the rating of the opponents. And here are some central tenets to developing this new yellow rating system. One thing we do is that scores in tournaments behave not as a measure of absolute skill, but fluctuates around your true skill level. And your score is going to be somewhat like a random variable that's dictated by your true skill. And we're going to base our rating solely on opponent ratings and the game outcomes, the games that you play with these opponents. And this rating is supposed to track the player's true skill as it evolves slowly over time. So unlike the practice rating, where a single tournament dictates the result of any rating, it's not going to happen here. It's going to have a more cumulative nature. And this is a really difficult problem to solve, trying to find a reasonable rating system. And I really like this quote by Yellow that says that the process of rating players can be compared to the measurement of position of a cork bobbing up and down on the surface of agitated water with a yardstick tied to a rope which is swaying the wind. There is so much variability and uncertainty. It's really hard. But they came up with something. So here's how their new rating system works. It's going to be computed after every game with just 3 numbers: your current rating, your existing rating, the rating of your opponent, and the game outcome. There's actually an auxiliary quantity that's computed as a result of some of these quantities, namely expected score. This is going to be a function of your current rating and your opponent's rating. And this expected score is a measure in the sense of how likely you're to win. You can think of this as a probability of winning, or the expectation of your score as a Bernoulli trial. The way this expected score is computed is quite interesting, and we'll cover this later. For now, just think it as a black box. I think of it as how well you're expected to do. Here's how the new rating is computed. You take the original rating you have, and you add a certain correction factor to it. This factor is going to be of this form k times s minus p, where s minus p is your actual score minus your expected score. Or you can think of it as how well you outperform your expectation. And k is going to be some arbitrary scaling factor that dictates how much rating change can be occurred after a single game. Choosing this k factor is quite hard. Mm-hmm. If you take this k rating factor as too small, then if you're growing rapidly, but not playing a lot of fun games, you could quickly become underrated because each game can only change your rating by so much, where your true playing strength goes skyrocket. Conversely, if you choose the k factor to be too large, then your rating could really tank after throwing a single tournament or even a single game, which is not good. And to choose this balance, there are a lot of considerations. It's mostly an arbitrary constant. And currently, the United the States Chess Federation gives higher rated players like masters, grandmasters, and such a smaller pay factor, which means that their rating would change a little bit more slowly compared to weaker players who have the potential to really outgrow themselves in a short amount of time.
So K is not constant within all plays at a tournament?
Yes. But if we assume that players in a tournament all have the same rating level.
Okay. Okay.
So just to recap this formula, it's very distant rating plus a correction factor that depends on how well you outperform your expectation, scaled by some scale factor. And now we dive a bit more into the expected score function. It's going to be a function of your existing rating and your current rating. Well, just intuitively, if your current rating is higher than your opponent's rating, you would probably expect your expected score to be more than half. You're more likely to win than you are to lose. And conversely, if you have a lower rating, then you're more likely to lose than to win. Here are some properties that might be convenient for this function to have. The second one is anti-symmetry. So because chess is a zero-sum game, or the way scores are currently having that it's a one-sum game, you would expect the expected scores of your score and the opponent's score to sum up to 1. And if you think a bit more carefully, you want rating to scale nicely. You want the same amount of rating difference to mean the same thing at the amateur level or at the master level. So maybe to simplify things, you actually want this function expected score to only depend on the rating difference between you and your opponent, not the absolute ratings. So right now we're down to function with a single variable, which is the rating advantage you have over your opponent, which we denote by D. And as before, we should have this. We should have the expected score as an increasing function of how much rating advantage you have over your opponent. And once we incorporate these constraints and try to sketch a curve of what it might look like, you get this following graph. As that graph, I intentionally did a very poor drawing because at this point we do not know the exact shape of this curve yet. A good question to ask is, well, what exactly is this shape? It turns out that the logistic curve works very well for this particular application, and it has the form 1/1 plus an exponential decay. And we'll talk more about why we have this shape. To derive what that shape is, we first introduce a useful quantity to keep track of, which is the odds of winning, or you can also think about that as the win-to-loss ratio. So in probability, if you have some event E, the odds of this event happening is defined as the ratio of this probability of this event happening to the probability of this event not happening. Or alternatively, it's the same thing as the probability of E happening over 1 minus the probability of E happening. Great. So in the context of win and loss in games, you can think of this odds winning as the win-to-loss ratio. And what this one answers is an actual question of how many times more likely are you to win compared to lose. And intuitively, if two players have the exact same rating, you would expect the win-loss ratio to be 1. It's more likely for either player to win as it is for them to lose. Now let's try to think about what the odds of winning should be if, say, you lead your opponent by D rating points. Just by plugging in the formula above, we could write that in terms of the probability of winning. We would denote this function the odds of winning if leading by D rating points. We would denote this function by omega of D, omega for odds, because I couldn't think of anything better. And this will be the probability of winning over the probability of losing, which is the probability of winning over 1 minus probability of winning. And probability of winning, as we said in the few slides before, is our function expected score P. So the odds will just be P of D over 1 minus P of D. The critical assumption that gives rise to the logistic distribution is that odds is a multiplicative quantity. So currently, just from the previous slide, if you're leading your opponent by D1 points in your rating, then it increases your odds of winning from 1 to omega of d1. And this is multiplicity change. You can think of this being once you gain d1 rating points over your opponent, it makes you omega of d1 times more likely to win. And now we can extend the statement naturally. Say if on top of this d1 rating lead, you also lead by another additional d2 rating points. Intuitively, it would make sense for your odds of winning to be further multiplied by the odds associated to d2. But if you're leading someone first by d1 rating points and then also taking 2 rating points, it's the same thing as leading that person by the combined d1 plus d2 rating points. So to put that into formulas, we would have omega of d1 plus d2, the likelihood of you are winning after a lead of combined rating points. It should equal to the product of the individual odds you have when you lead by d1 and you lead by d2 alone. And it turns out that just having this relation alone, it forces the function omega of d to give a certain form, namely an exponential function, where the base is an arbitrary constant. And if interested, we could go into detail at the end for why this follows. Now the logistic curve follows quite naturally. So in the previous slide, we deduced that omega of d has to be the form of an exponential function. But previous to that, we also wrote omega of d in terms of the probability of winning or the expected score, which is expected score minus 1 minus over 1 minus expected score. Once you have this, you can set them equal and solve for the expected score and get exactly this, the logistic curve. As mentioned before, b is an arbitrary constant. You can choose anything for b really, and the relation still holds. But in practice, b is usually chosen arbitrarily to be this factor. 10 to the 1 over 400 is arbitrary. It's just to make things scale nicely. And this is approximately equal to 1.005773. This is a plot of what the expected score looks like as a function of rating advantage. As you can see, if the rating advantage is 0, you and your opponent have the same rating, the expected score is at half. It's going to be pro-ish. If you're leading by 200 points or down by 200 points, you are visibly more likely to win than to lose or to lose than to win, but it's not completely decisive. Let's say if you're leading someone by 600 points up here, there's a very good chance you're going to win. All of these ratings we've discussed so far, which include the Hart's rating system and the yellow rating system, they are both comparative ratings, meaning that these ratings compare you against your peers, not against some absolute gold standard. So, for example, the yellow ratings compute solely from your existing ratings of you and your opponent and the game result. It measures you against your peers and does not, on any account, measure the absolute scale. If magically someday you and your opponents all leveled up by some fixed amount of scale, in scale, then the ratings are not going to change because it's a relative measure. And one curious property about the yellow rating system is that after each game, it doesn't matter how much rating points you gain or lose, your opponent loses or gains by the same amount. So at the end, just like chess is a 0-sum game, the sum of yellow ratings is actually also the net change in yellow rating is also 0 after every single game. So if you have a closed pool of players playing against each other, the average rating of the pool will just stay constant. That could be a problem if you want to measure the skill of the player in absolute terms, because well, players keep improving, but their ratings are stuck where they are. And you might want skill in absolute terms to be somehow reflected in the rating. And one of the mitigation measures taken by various online chess websites and federations is we are going to assign new players overly high ratings. And when this new player plays a lot of games against established players in the pool, they're going to quickly shed these extra rating points away into the pool. And this influx of extra rating points will help balance out the deflation. eventually before there are these issues with comparative ratings not being able to objectively capture the absolute skill of a player. In the modern day, we have chess engines that form outplay humans and give almost objective evaluations of position. So it might be interesting nowadays for people to invent metrics that attempt to capture absolute skill compared to best play, as opposed to a measure of your skill compared to relative to your peers. Most prevalent such new rank system based on engine play is called the average centipoint loss. To understand what this is, we first need to understand how computers evaluate a certain chess position. So the computer takes in a certain game state, the arrangement of pieces, who it is to move, and so on, and spits out a number. And this number is spits out is based on a lot of different factors. Some of them are going to be material count. How many pieces are you up by, and how good are these pieces? Also, activity of the pieces. Are they stuck in the back, or are they in good attacking position? How safe is your king? Is it safely hidden away behind our pieces, or out there in the open being hunted down by your opponent? And are there long-term structural weaknesses that might lead your position to disintegrate over time? There are a lot of these factors, but one of these factors seems more quantifiable than others. Anyone cares to risk a guess? It's material count. You can physically count how many pieces are there, and you can assign relative values to pieces, whereas for the other ones, it's not clear how to encapsulate all of that information you just done. So what the computer evaluation does, or rather tries to do, is to take all of these considerations into account and produce a single number that reflects what would your advantage be if all of these different forms of advantage could be converted into material advantage instead. And this unit for the net equivalent material advantage would be in centipoints, which is 1/100th of the. And after each move is played in this game, the evaluation of the computer changes, where if you play the best move according to the engine, it preserves your current evaluation. But if you play any move that is considered suboptimal by the engine, your advantage, the evaluation goes down by some amount. And this amount is called the centipoint loss for this move. And what the average centipoint loss measures is how much do you lose, how much centipoint, what is your centipoint loss per move on average. This average could be across a single game, across other tournament games, or over all games you've ever played. And a stronger player would correspondingly have a lower average centipoint loss. They give away less advantage per move on average. Here's an example of how centipoint loss works taken from one game. The first position, the computer gives an evaluation of 8.7. That's huge. If you count all the pieces, black and white actually all have the same pieces. Any guesses for why the evaluation is so high in black's favor? Black to move, by the way.
2 knights out and moving.
Yes, development is also a factor. It turns out that in this position, there is a safe tactic. If you play bishop to f2, there is no option for white other than to capture the king. And once the king goes here, that's a free queen. And that gains you a huge weighted material. So despite the material being equal right now at the moment, the computer sees that line and thus concludes that black is advantageous because black could play that move.
Which was the move again?
Bishop to f2 check.
Okay.
Or if you're not really paying attention, you're just nonchalantly doing like the development move or castling, suddenly the computer evaluation is all the way down from 8.7 to 0.3. Castling is considered a suboptimal move by the engine because you missed the chance to trade the bishop in for a queen. So the centipoint loss for this move would just be the difference in evaluation times 100 because we're measuring it as centipoint, 100th of the point. In this case, you lose 840 centipoints for this move, which is huge. And here is a nice example of how evaluation could change over the course of the game. The first plot is a plot over time, where time is measured in which move it is in the game. It tracks the evolution over time of the computer evaluation, where the first game is taken to be an almost perfect game played by two modern day chess engines. And you see mostly just flat. It's okay, maybe white's a tiny little bit better near the beginning and quickly fades away. And after some point, the computer just knows that there is a forced drawing line and just thinks the game is completely drawn. No hopes of taking winning. The second plot is a game at the presenter's level. It's one of my games from the past. There is a lot more exciting stuff going on compared to perfect engine play. There are lots of blunders by black, increasing the advantage in white's favor, but also blunders by white, making the advantage go in black's favor, and eventually white makes too many mistakes and ends up losing the game. So compared to the previous flatness you can see here, we see a lot of up and down fluctuation, where the more frequent the fluctuations, the more errors are present in this game. The last plot I find very amusing. It's, according to Engine, the worst possible chess game you could ever play, where you play the worst moves instead of the best moves. You cannot see anything here. It's just this massive orange blob. But what's actually going on is the lines are just going up and down so quickly, the computer doesn't have enough pixels to display them in detail. And now look at all the second on the loss ratings here. For the perfect computer games, both sides are losing about 3 or 4 second points per move. That's tight. That's better than most humans could do. On average, in fact, it's better than any human could do. And for one of my games, the average second point loss is like 30 or 50. So about once in every 2 moves or less than every 3 moves, a giveaway advantage that's equivalent to a point. That's not great. And if you look at the worst possible game according to the chess engine, the average second point loss is about 2,000. So you can see about 20 pawns worth of advantage per move on average, according to the computer. If any of you wants to see this game or wants to learn how to play it like this afterwards, talk to me after the presentation. Well, every second point loss was developed as an attempt to measure the skill of a player objectively, but it turns out that it fails in many different ways. It's not actually objective. The precise evaluation of the position is going to depend on the exact engine you're using to do the evaluation. And as engines become more and more powerful as time goes on, they're able to spot more and more ways to win from a position where it looks like neither side has anything to do. As a result, for the same position, the evaluation keeps getting higher as engines get stronger. So, for example, you cannot compare evaluation from one engine to the evaluation of a different engine. You can only compare with the same engine. Another issue is that just from a purist kind of standpoint, evaluation is objectively not a continuum. Given any position, either one of 3 things must be true. Either you can force a win, that is, you can force checkmate in a finite number of moves. Your opponent could against you, or the game draws with perfect play. So if you imagine an infinitely powerful chess engine that can see through all possible moves in the game, then the evaluation it's going to give is only going to be one of these 3 forms. And there is no such thing as a slight advantage objectively. Either your advantage is so small that your opponent can draw against you a perfect play, or your advantage is crushing and there exists a way for you to force checkmate. That naturally raises the question of, well, how much material is a forced checkmate worth? Because remember, what this average second point loss is based on is an evaluation position where it tries to convert all forms of advantage in terms of material advantage. Currently, there is evidence to suggest that the current system has to work 10 points because in the previous game, white and black just alternated blundering into 1, and the average second point loss was around 2,000. And another factor that comes into consideration is the fact that this average second point loss quantity, it depends on not just the skill of the player, but also the style. Do you like to play open or close positions? Do you like exciting, fast tactical games or slow maneuver games? If you like to play sharp positions, then not terrible for you because by definition, these positions are very prone to sudden mistakes because suddenly hang a piece or suddenly lose to a checkmate. These positions are more prone to decisive blunders, which means they tend to end very quickly, so few numbers move. And also, there's a very good chance you could concede a lot of advantage by playing one move. So overall, if you like to play sharp positions, you're gonna it's likely for you to get a very high average sentimental loss count. Where if you're on the other end of the spectrum, where you like to play very defensively and you like to play closed positions with lots of maneuvering. For one thing, these games tend to be much longer because things in these games take a long time to happen. But also in closed positions, it's less likely for someone to suddenly blunder a piece. And in these games, you can artificially lower your average sentimental loss playing these games because, for one thing, you are less likely per move to make a blunder. And also, these games last longer, so there are more moves in the denominator. And we see that all these rating systems is perfect, and that concludes our presentation. Here are some resources, including Chess Journal, this book by Neil himself on the rating system, and some blog posts. And right now we could go into derivation for why the odds of winning has to have an exponential form. I find this very fascinating proof. What we're trying to do, we're going to replace omega with x because it's easier to say. We're trying to solve essentially the functional equation f of x plus y equals fx times f of y. How do we approach doing something like this? Well, we can first try to narrow down what f should be for 0. If you take any real number x, you can write x as x plus 0. So according to this expansion rule, you should have f of x equals f of x times f of 0. Well, if f is 0, if f of 0 is 1, then this holds for all x. And if this doesn't happen, then you would have f of x equals itself times something. Doesn't matter what f of x is, and that would force f of x to be 0 for all x, which that's trivial. We don't want that. Okay, so now we know that f of 0 is 1. That's good. Now we move to determining the value of f on all positive integers. Using this expansion rule, we can write f of n as f of n copies of 1 added together. And by this expansion rule, it's the same thing as multiplying together n copies of f of 1. That's f of 1 to be. The next step up from positive integers, we can do positive rationals. So we take some arbitrary positive rational number p over q. The trick to doing this is we take the f at that point and we raise the resulting valuation to q. So what we have here is q copies of f of p over q. We multiply all of this stuff together. And by our combination rule that the function has to satisfy, this is the same thing as f of q copies of q over q added together. Well, q copies of this thing added together is just q times q over q. So at the end, it equals f of p. So at the end, we have f of p over q, all raised to the q equals f of p. That once you raise both sides by a power of 1 over q, you have f of p over q is f of p to the 1 over q. But we know what fp is. Fp is f1 to. So f of p over q would be f of 1 to p over q. We're seeing the pattern here. F something looks like f of 1 to f something. Now we have f for positive integers and positive rational. Next step up is this actually suffices to determine what f is on the positive reals because the rational numbers are dense in the real numbers. And if you want f to be a nice continuous function, it turns out that you have to have f of x equal to f of 1 to x for any positive real number x. And now, finally, we could do negative numbers because we can write 0 as x minus x plus x. So we would have, by this expansion rule, f of 0, which we know is 1, equals f of minus x plus x equals f of minus x times f of x. So f of minus x ends up being the reciprocal of f of x, which agrees with what we're trying to solve here. And that concludes the presentation. Any questions? Also, I'm going to leave this nice puzzle on the board. Just want to move to 6.
So, in any of the chess rating systems, it's just at the end of the day, win or lose, nothing about how competitive you were in the game.
So far.
At the end of the game.
What do we mean by how competitive you are?
So if it takes somebody, 60 moves to finish you off, that's a much better fight you put up than losing in 10.
That's a really interesting consideration.
This doesn't look at all where you, and again, one of the dangers is you do not want to create a metric where you reward somebody for calling check, because now you might have people who will, I'm not going to win this game, but I can get you in check. I'm going to lose my queen in doing this, but
yes, I think this is probably intentional, actually.
Yeah.
Probably for the same reason why others people lost that idea. If you choose to play the defensive style, the games are going to last longer.
Right.
Yes, none of these current racing systems take into account the length of the games.
And again, that's, you would want to have things in different equivalence classes. For example, I'm going to eventually nurse a 1-pawn lead, and it's going to take me a while to march down the pawn and score. And then, but if the game is in under 10 moves, if it's 10 to 20 moves, some broad categorization where you don't have sharp cutoffs as you go from one to the other. This is how we get to Williams has, oh, this is being recorded. Wonderful, wonderful caps of 19 for completely educational purposes in a lot of our classes. And then it is unknown for those of you who do not play chess if it's an advantage to be white or not. It is not believed to be a disadvantage, but I believe there's no proof of that yet.
Yeah, right now the engines are not quite strong enough.
Yep.
Questions, comments, thoughts? Yes.
Are there any talks to maybe tweak the engine system that's used depending on the ratings of the players that are playing? So like, if the engine can exhibit perfect play, then it might make more sense to use that sort of engine for grandmaster matches, but it may be using some sort of database of like say 2 players are playing with ratings 500. So maybe a database of games that happened with those players, because obviously a 1-pawn advantage wouldn't mean nearly as much when really bad players versus really good players.
I like that suggestion. It's very sensible because if you're only using engines to evaluate master level games, you're not going to have someone suddenly wondering making one. You run into problems like how much material is making one.
Or just you might have a, say, 5-move attack that's going to net you a queen. And so at this stage, you've got to be the grandmaster to see the chain that's going to start and get there. And if you do something else, which almost everybody else would do, well, you've just lost a tremendous amount of points relative to what you could have had. But when you consider who you're playing with, this is the slow and steady strategy that will give you a win in what you're doing. And so really what matters is where are you at the end of the game. It doesn't matter where you are in the middle of a game. You can use this to try to make assessments about what you're doing. Am I at a disadvantage? Do I have to do something risky? I think one of my favorite examples of this in sports, and there should be at least one person here who will correct me. I think it was Colts versus the Saints in the Super Bowl, where the Colts were predicted to win. And so the Saints, for the first time ever, did an onside kick to start off the second half and succeeded because they go, look, we are in the weaker position. If we play the standard game, we will have a respectable loss. We're not going for a respectable loss. We'd much rather have a squeaker win and risk being humiliated and having a large loss than this safe strategy of trying to lose by just a little.
Actually, it's quite common in chess in terms of games.
Mhm.
Just imagine athletes at my level, if you're playing someone you know is averagely stronger than you, you don't play the solid moves. You play something a bit crazy to take them out of the prep.
Yes. If there's no questions, then I will say something. Okay, so I'm going to end the recording.